Hi everybody, welcome to part 2, which is going to be the final part of the Phase Linear Model 400 Series 2 restoration. So in the first video we just kind of looked things over a little bit, and it generally, the amplifier worked. It had a couple little issues but nothing major, and so I thought I would go through, and in this video we're going to make some improvements to tame the flame. These didn't get the name Flame Linear for nothing. If you look in the comments of the last video on this, many people said, hey, I had one of these when I was young, I loved it, but it blew up. It burned up my speakers. It go down, just go down the line. And the reason being is a lot of the safety things that you see in the later amplifiers, like the Pioneers, the Marantz, all that stuff that kind of came after this, kind of took after some of these designs, they just didn't exist in this amplifier. Now the first one, the Series 1, the one that had the differential discrete input pair and all that, those were even worse. But once they went to the op amp, that just added more problems. So we're going to kind of see, I'm going to do my own take on this. And I know that there's that company out there, I think it's Oak Island or White Oak, I think it's White Oak. They make an entire upgrade for this that you can just tear all the boards out and put everything in. It's a lot of money, but it fixes all the problems and makes this a really reliable amp. But I want to keep this one more original, see what I can do with it, and see what kind of results we get. So if that sounds interesting to you, stay tuned, and let's see if we can tame the flame. Okay, I hope you can see this. There's always someone that's going to complain they can't see because their screen is too small or the resolution or whatever, but I'm filming this in 4K, and hopefully you can see it. I'll try to zoom in when necessary. But anyhow, anything that's circled in red are things that I added or changed. Any, like major changes. Anything written in red are components that were, different, have been swapped out for a different version of some sort. So let's start with this front end here. Now, I put a decoupling cap at the front end of this, and I set it to, the biggest one I had that was a good size to fit the board was 4.7 microfarads. This isn't super critical. It can be a higher value than this. You just don't want the value to be so low that whatever this input signal and whatever current you need for this, which is extremely low because this is super high impedance JFET input, through this, look at, you have a 10K and a 39K in series. So you just need to make sure that the capacitor can deliver the current at the frequency, using, you can use the capacitive reactance formula just to make sure that it exceeds that. So this is more than enough. Why did I put that here? Well, right now, if you put a DC level in here, it would put DC here, and you would have a DC level output on that. A lot of people design their amplifiers that way because they're trying to get the the best response, the best frequency, the best sound, blah blah blah. I don't believe in that. For the tiny little bit of sound quality you would lose from having this in here, I like having this safety feature. If something fails on your input source and you have a DC level put here, it's going to ensure that this cap will just charge and discharge, and then you will not get DC out here. Yet if you put a low frequency in here, this capacitor is high enough capacitance that it will pass that low frequency AC signal, if that makes sense to you. Again, it's optional. If you don't want it, you don't need it. It worked without it. For the chip itself, I removed the LF356, which has a higher quiescent current than the one I used, and I swapped it with a TL071. I call them TLO71 because it's faster to say, but it's actually a TL071. They're very cheap. They're readily available. You can also use one of those OPA chips like I think it's an OPA 2134. Opa! Yeah. Hello, Opa! Okay, never mind. But I don't really think it's going to make that big of a difference because, again, very high, you know, much better specs than the 071, but I don't think in this application you're going to notice that big a difference. This thing has a gain bandwidth product, the TL071, I think somewhere around 5 or 6 megahertz, which is way above where we're going to need it to be. So it's already overkill. You know, it'll be just fine. This 100 PF capacitor I put in here, I put a note here. It's actually an experiment that I did. In that this is your global negative feedback. It also deals with your offset nulling and so forth. This timing circuit kind of takes the offset out, the offset action out while there is a signal being driven into here. But as soon as it settles to a DC level, or if it's a very low frequency, something that's, you know, way off, you know, on for a long time, then this will charge up, and then it will allow the offset to act. Okay, this feedback, if I have something in here that's high frequency and it comes out here, it can come right back into here into the negative feedback and clamp it out. Being 100 picofarads, it's so tiny that it won't affect any lower frequencies. But when you start getting up into the megahertz, this is actually going to pass some of that signal back. So what does that mean? Well, if the chip somehow internally starts to oscillate, if you somehow have some sort of an oscillation at the input of, you know, pin 3, this is going to help squelch it out a little bit. Again, I don't know how much effect it has. I know that it did not cause any problems by being in there because I have it in there right now. Again, it was just something I wanted to mess with and see. Okay. A lot of these things, you know, you just try it and see what it does. The power supply for this chip, it was ridiculous the way they did it. They basically, you had these 5,900 microfarad capacitors, these giant filters, these guys right here, and you came straight off of that through a couple of resistors. So here's your B plus, B minus is just the same thing. Goes straight into it was originally a 1.8K resistor. It's now 7.5. I changed it to. It gets shunted by this shunt regulator, which is nothing but a 15-volt Zener diode, and then goes straight into the chip. No bypass capacitors, nothing. I mean, you're just asking for this thing to go crazy on you, and that's why it wigged out so much. That's a bad thing. So what I did was I took you don't need much because these are super low current devices. I took a 100 nanofarad film capacitor. I connected it directly to pin 7 and then another one directly to pin 4 to ground. You see, here's this one drawn here, but this is actually connected right on the pin, and this one is connected right on the pin. And that just gives you a little bit of bypass for any kind of noise coming from that shunt regulator. Now, having this be a low quiescent current chip, you know, the TL071, I was able to reduce this just like they did with the LF351, which is very similar to the TL071 when it comes to that. And by dropping this, you lower the current quite a bit through here, which keeps this running cooler, so this isn't going to drift as much, and you're going to have less ripple, especially with this bypass capacitor. So that's why I did that, if that makes sense. Down here, I increased the filter capacitors from the 5,900 that they were, right, at 85 volts to a 12,000 at 100 volts. Now everybody's like, Tony, why don't you put 100 million microfarads in there and it'll open the sound stage? And the 12,000 is perfect for this. It'll work just fine. This is a big, heavy transformer. And remember, this only has to fill in the gap for that transformer for about 8 milliseconds as the as the waveform of this crests up and down and recharges the cap. So you're not, between those pulses isn't a very long period of time, and that's plenty of capacitance for this particular amplifier, as we've saw in our tests, as we've seen, I should say. All right, at the input of this, because we put bigger capacitors, we don't want a lot of inrush, especially since this thing doesn't have a power switch on it. You plug that into the wall like this, you're going to draw a big spark on the prongs of your plug, and you're going to ruin your outlet, in your house, and you're going to probably burn up the prongs on the plug. So by putting this thermistor in here, or I should say this is a ICL, or inrush current limiter. That's not the right term I have written there. It's a model SL32, and this will limit the inrush current through the transformer as these caps charge up. This relay is connected in series with a 10K 5-watt resistor. You have to use exactly an Omron G5Q-1A4 DC22 relay. If you use a different relay, this coil will draw a different amount of current, and you will have to change the value of this resistor to provide that proper current and voltage drop across this coil. Okay, so this is specific to this. It connects over to here to the B+. As the capacitor charges up, once it gets up 65–70% of its charge, it's going to pull in this relay and bypass this and allow full current out to the transformer. That's what this does. Okay, so this is one of those little circuit boards that I built, and you've seen me use it 3 or 4 other times in other projects. It's just that same board I used on this one. Moving over to here, I put a little note about the bias control. This is a Class B output. It's quasi-complementary, meaning they're all using NPN. These are those XPL 909 or whatever they're called, 109, I forget the name. But they're NPN, old school transistors. They're very good quality, and they're all original, and they're in good shape. These are those RCA transistors. They're similar to these. They're being used as drivers. And you can see when you run these things in Class B in a quasi-complementary amp, these do not have any idle current. So when you're sitting idle with no signal and you try to put your meter across these to measure the voltage drop to see what your bias current is, it'll say 0 or close to 0. And you'll adjust that pot till you're blue in the face and nothing will change here. That's because the only thing that has bias current on it is these transistors here. And you see there's a little 10 ohm half-watt resistor. You measure your voltage drop across that, and that shows you the base voltage of these. And you want to set that to about 400 millivolts. When you set a 400 millivolts at this point, you're holding these at 400 millivolts. When does a silicon transistor turn on? Somewhere around 600 to 650 millivolts. So this is just at the brink of turning on, okay? And what's going to happen is this is actually operating in Class B, meaning these are going to turn all the way on and all the way off throughout the work cycle of the midpoint here. That's how it works. Well, why don't you get switching noise? Well, it's because of the way these are almost turned the whole way on, okay? And they will overlap as they turn back off. So believe it or not, it works really well. But you just have to understand that setting the bias, you set the driver bias current, not the outputs on this type of amplifier. All right. Coming out to here, the original design had this Zobel network, and it consisted of a 0.1 microfarad capacitor and 2 10 ohm 2 watt resistors in parallel, giving you 5 ohms at 4 watts. And that was the only parasitic oscillation suppression you had for out here. Normally you would see a snubber network after that, in a lot of amplifiers, and I added that. And you can see I built my own, and I used 22 turns, so I just wrapped a wire 22 times of number 18 magnet wire on a 1/2 inch form. So you just take like a 1/2 inch drill bit or a 1/2 inch piece of metal tubing or a 1/2 inch dowel, and you wind it around there 22 times, and it'll come out looking something like this. Then you take your resistor, and which is 10 ohms at 2 watts, you run it through the middle of this, and then you just tack the leads on this end and this end, and then that is your snubber network. This is going to come out to somewhere around between 2 and 2.5 microhenries, 2 to 2.5 microhenries, plus or minus a little bit. It's not super critical. Okay, these two circuits work in conjunction with one another in order to suppress any type of oscillation that you might receive because of the crossover. Some speakers have really weird crossover networks in them with caps and coils and resistors and all these things, and then you put that in conjunction with the voice coil of the speaker, you're going to have a mess. And sometimes you can get parasitic oscillation, and we want to avoid that, and that's what these two circuits do. From there it goes into just one of these generic, let me show you. One of these boards here, you can see, I don't know if you could see the little number on it, www.xd218.cn, but these are readily available on eBay, on Amazon, on AliExpress, all kinds of places. You can find this same board. And the thing I like about this one is it has this little switching power supply that you can put anywhere from 85 volts AC to 265 volts AC, and it provides its own power supply. The other ones that you normally get require an external AC power supply, somewhere around 12 volts AC, and not every amp has that available. And even the ones that do may not have enough current, or they may not like being paralleled with the power supply, that's usually regulated for the tuner or for whatever it's using. So this eliminates that. It also uses the AC line for that zero crossing that you're going to need to make this thing work, because this needs an AC signal as a reference. And this is using one of those UPC 1237 speaker protection ICs. These are great. Okay, these are mass produced. You can find them anywhere, and they work really well. 2 nice heavy duty relays, and this provides a couple of things. The first thing it does is it will give you a delayed connection to the speaker. So when you first turn this thing on, this thing powers up, and it's going to wait several seconds before it pulls these in. It's going to have an on delay. So it's going to keep the speakers disconnected from the amp, so you don't hear that big thump when you turn the amp on. When you turn the amplifier off, it immediately disconnects the speaker as soon as the AC line is gone, to get rid of the turn off thump. It also monitors the center terminal here with reference to ground to look for DC offset. If your DC offset exceeds like about 1 volt, it'll drop these out and disconnect the speakers. So if a transistor dead shorts and you have your 80 volt B plus straight onto this center line, it'll disconnect the speaker very quickly and save your speakers from burning up. I will not connect good speakers to an amplifier that does not have something like this. There's different ways of doing this. You can use a MOSFET, you can use a relay, a couple different things, but whatever the case may be, you got to have a speaker protection circuit, which this does not. This is how it got its name, flame linear. You have an unstable circuit that can oscillate, and you have no speaker protection, and if something shorts out, you're going to trash your speakers, and this gets rid of that. This is now a very stable and reliable amplifier, and it will work really well for a long time. Okay, let's take a look at this schematic for a minute. Something interesting I noticed was So here is the midpoint, where this is the line where your speaker would be connected. So if you go out here, see that's where all of your speaker terminals are. And if I come back over here, that comes back through this 12K resistor. Sorry about the print there. And it goes through here and down into pin 2, which is your feedback. That's your negative feedback, or the inverting input of your op amp. It also goes through this RC time constant, which is a 270 ohm resistor and a 100 microfarad, and this is supposed to be 6.3 volt capacitor. There's some problems with this circuit here from the design. The first problem is if you drive this amp to full power, which, you know, it's full 200 watts per channel or whatever, you can have a signal swing of plus and minus 15 volts. And yes, the voltage can go positive and go negative. So technically you could reverse polarity this capacitor. Now, there's a lot going on in here that makes that not be as big of a problem, but just understand, if one of these rail voltages, let's say something goes wrong and this goes to its full rail, so one side turns all the way on, like a transistor shorts or something like that, you're going to put that whole rail voltage through these resistors, and if you do the math, looking at this as a short when it's charging up, or if it's reverse biased, you're going to draw about 6 milliamps, somewhere around there, through this capacitor, current limited by those two resistors. And as I said in another video a couple series ago, you can reverse polarity a polarized capacitor, and it will act like a capacitor, but at some point it will eventually become a short. But at very low current and lower voltages than its voltage rating, you can get away with it. And that's why you'll see polarized capacitors like at the inputs of these, because, you know, they'll put a 50 volt cap in here, and you'll see the maximum voltage in here is going to be, you know, less than 2 or 3 volts RMS, and that's how they get away with it. Well, that's not really the case here. You can actually force this into shorting by doing that. Now, what's the point of this whole thing? Well, this is a timing circuit. Remember that another purpose of this IC is not only just to provide the global negative feedback through this inverting input, but it also, this chip is what's responsible for your DC offset null. So this is what keeps the midpoint at 0 volts. And it does so by kind of monitoring these two things and then trying to bring them balanced. And what happens is, if you didn't have this in here, as soon as you put a signal in here, that signal would act with that, and your offset would be always trying to fight with the circuit. So what this does is this basically puts a time delay on when the offset is going to react. At least that's how I'm seeing this the way it is. It's an RC time constant. And the time constant of this circuit here, if I'm not mistaken, is somewhere over 1 second. So like within 1.5 seconds to 2 seconds, then it'll start to change. But if you have an AC signal going here, this acts like it's not even there. It'll ignore it. So bottom line is, this should be a higher voltage than 6.3, because theoretically you could have a potential of up to about 15 volts here, just the way this whole thing works. And we'll look at this, we'll measure it here in a second. And additionally, for added measure, even though this obviously does work, the cap that they had in here was 100 microfarad at 10 volt. That was the original one that came with this. Let's see if we can focus on it. There, you see it? And I'm going to change this out to a higher voltage capacitor. I'm going to go to 16 volt capacitor, and I'm going to change this to a bipolar capacitor. So you can see that's what I've done here. Now let's kind of see if what I'm saying makes sense. So first of all, I'm going to put my meter in here, and I'm going to try to get everything kind of in shot so you could see it all. There we go. And I'm going to put my red meter probe right here on this 270 ohm resistor. I'm going to measure this, and I'm going to show you what happens when we turn the power on and turn the power off. Now, we're not going to put any signal into the amp yet. We're just going to look at power on and power off and see what happens at that juncture, which is basically what's going to happen on that capacitor. Okay, so let me get the probe on here. I'll just touch either channel, it doesn't really matter. So you can see I'm on the test point, and I'm going to flip this on and watch what the meter does. See how it jumps and then it goes to 0 right away. After about a second, it nulls out, and you can see we're at less than 1 millivolt now. Now watch what happens when I turn this thing off. Right now, turning off. You see that? It shoots up, and then it drops. And as that capacitor discharges, see how it goes back and forth until the big filter capacitors bleed out the whole way. But you can see for a split second, you can have quite a bit of voltage at that midpoint. Now, let's move that out of the way, and let's look at what the waveform looks like when we apply a signal there. Okay, I'm connected to the same test point, just on the other channel, so that my meter probe ground lead can fit easier. And you can see right now, even after this has been off for a minute, it's still bleeding off. You can still see it's not sitting at 0 volts, because I have this set to DC right now. Now watch what happens. We're going to turn it on. It goes right off, and there we go. And you can see right now that everything is sitting there. Now for a moment, until it stabilized, you saw it just a tiny little bit of noise on there, and that was just noise. It was no big deal. All right, if I take this to ground, I'll center this a little better so that it's right on the center graticule, huh? There we go. Now go to DC, and you can see there's no signal on there right now. If I turn on sine wave, you can see there's your signal. And again, I'm at 200 watts per channel, right? I'm swinging this to the maximum rails. And if you look over here at the scope, I'm at 50 volts per division. See that? And I'm at almost 45 volts RMS. That's a lot of power right there. If this was I'm not driving into a load yet. We're driving open terminals. And you can see if I turn that down a little bit, it'll settle. But there it is. So you can see right now, if I crank this all the way up, just before clipping, I'm right at the edge of clipping. You can see I'm at 5 volts per division because I'm on a 10 times probe. I'm sorry, I'm at 0.5 volts per division. So it's about 1.5 volts of swing right there, right now. Okay, so during operation, it doesn't go as high, but when the amplifier is turned on and turned off, it will swing up past that briefly. But you can see right now we're looking at about 150, 1.5 volts. Sorry about that. About 1.5 volts. All right, and since it is going positive and negative, that capacitor will prevent that offset adjustment from activating. So you turn it back off, and you can see it brings it right back to 0 volts immediately. So that timing circuit is critical. If that capacitor were not there, you would have a lot of problems with it. Okay, so that's how that works. Now again, if I turn this thing off, watch this line will just shoot right off the screen. Turning off the amp now. Boom, gone. And I can turn this, there we go. I'm now at 5 volts per division, so we're still, see how it goes down and back up? That's because the big filter capacitors are discharging, and the op amp, the voltages on the op amp are not normal now because the caps are bleeding down. You can see slowly as the main filter capacitors bleed down, so do the voltages on the op amp. Okay, let's look at our dropping circuit for the for our shunt regulator. So the anode of this zener is going to be your negative voltage supply, your minus 14 volts, and see, it's, or minus 15 supposedly, but these are about 14.5 volts. And then the cathode of the other zener diode is going to be your positive supply. You can see it's positive 14.4, so it's very good there. And remember, the original design of this had a different integrated circuit. It had an LF356 or instead of the 351, and those require a higher current, quiescent current. So these dropping resistors had to be a lower value. So if you look at the original schematic, they were 1.8K, which was these green ones right here. And these got pretty toasty, and you can see where it kind of scorched the board a little bit on there. And these new resistors, they call for 7.5K, so that limits the current quite a bit. And I didn't have any 7.5K 5-watt resistors, so what I had was a 15K resistors at 5 watts. So if you take these two 15K metal film resistors and put them in parallel, that gives you 7.5K, and that's why these are like this. And I made them hang off the side of the board, so if there is any heat, it won't put it on the board and it won't put it on these zeners. Because as these zener diodes heat up, their zener voltage will vary, will change. We don't want that. And I can hold my finger on these all day long, and they don't even get warm. They get just above room temperature. That's it. They stay very, very cool. And same thing with these op amps. They don't get warm at all because, again, they're running on very low current. Now looking over here at these two capacitors, these are 4.7 microfarad film capacitors in series with that 10K, and I put really high quality, high precision film resistors for the inputs. So these are going to be low noise, and yes, this little connection is sticking out. It's not going to hurt anything, okay? You're not going to get noise. I know somebody's going to go in the comments and say, Tony, you're going to create noise, and my sound stage is going to shrink, and it's going to sound terrible, and everything, and I don't know what to do, and you ruined it, you ruined it. Well, no, it's fine. It's just fine. Calm down. So that's what this is. Here is the voltage amplifier stage, and these are those, I'll show you the updated schematic again we'll go to, and that's going to be these KSC 3503s. Those are replacing those funky looking ones in the big metal things with the steel on them. These are a lot more robust. They can take a lot more punishment. They're quiet. These little heat sinks, I was questioning whether they would be enough, but they are more than adequate. I've driven this amp really hard, and these barely get a little bit warm. So they're going to be fine. These ones can also be replaced, similar like KSC 3503 and the complement to that, which I don't have off the top of my head. And you could do the same thing. And you notice by standing them upright and using these short heat sinks, which you can buy on eBay or wherever, you could do the same thing here and here on these and replace them, and they'll fit, and that'll work if you need to. These are in perfect condition, so there's no need, and they're very high quality transistors, so there's no need for me to replace them. Here's the voltage converter transistors, the MPSA 93s, and those are right here. And you can see right there. And I'll show you these on the back of the board how I did it. You know, right here and right here. It's important that you put these right on the pins of the chip. This one down here and this one here. They have to be directly on the pin of the chip to do their thing. I'll show that to you right now. Okay, here's the underbelly of the board, and a couple of things that I did. This capacitor was just a normal ceramic. I replaced it with an NP0 just because of how tiny the capacitor is. It doesn't really matter if it drifts a wee little bit, because all this is doing is it's preventing the transistor from going into oscillation. Okay, it's kind of bootstrapping this a little bit, and it also gives you a little bit of feedback to prevent the transistor from oscillating. But really, for it to be the most effective, you want it to be right on the pins of the transistor. So here you go. Right there's where I put it. They're really tiny. See that? They used to be all the way over here, and then you had all these traces winding their way around to here. And that's not good. See, this one goes all the way up here and all the way here and all the way here. And this one goes all the way from here, around here, and into here. So I just put it right there on the transistor. The power supply bypass caps, which would be this 0.1 right here and this 0.1 right here. Those are right on the back of the chip. And then I had to pick up the ground over here. So there's your ground, but they're right on the chip once again. And then this unnecessary cap, I'll call it, is right here underneath it. You can just barely see it in there. See the one there, and then the other one is right here. You can see it. And that's it. And other than that, you can see wherever the traces were really, really thin, I kind of reinforced them with some solid silver-plated tinned bus wire. Kind of a couple places where it just was so thin. These traces are so pencil lead thin. You know, I don't know why they didn't make these traces a little wider. I mean, they didn't have to be that narrow, but that's just the way it is. It's a very flimsy board. Yeah, this probably would be a good candidate to put conformal coating on the back to just kind of protect it a little more, but that just makes it harder to work on if you need to replace something. And then you can see I had to remove every one of these wires and resolder them, restrip them, clip off the ends, because these wires get work hardened from bending and kind of flexing over the years. And every single time I moved this, one of them would break off. Just looking at it, it would break off. So I had to basically take all of them off one at a time, skin them back, clip off, get some fresh wire, tin it, and put it back onto the pads. And now they're a lot more sturdy. Okay, picking off the voltage to go to our speaker protect module. One lead goes to the AC mains there, and you can see that would be this point right here. The other one's going to be down here, and it's just pulling it right off of the negative side, or the neutral side, whatever you want to call it. There is no neutral on this because it's a non-polarized plug. That's what that is. Our soft start circuit is located right behind the capacitors here. So if I take this out of the way, you can see it in there. Here's the inrush to the ICL current limiter, which is this one's an SL32. Here's the bypass relay, and here is your dropping resistor for the relay coil, and there's your positive going onto the 80 volt rail, and there's the negative going to the ground rail, and then your AC comes right off of the power cord down here and goes into one side of the board, comes out of the board, goes through this wire and to the fuse holder. So that's just how it goes. Okay, so it's very simple how it works. Okay, and how it's written in the schematic is a little bit different than how I did it, because I just didn't want to disrupt any more wires than I had to. So the power cord actually goes into the board first and then comes out of the board and through the fuse. So just swap these two around. Tony, you got to have the fuse before everything, or it's going to cause problems, and it could catch on fire and blow up, and you'll get sued, and everybody will die. Yeah. Well, I don't think I would worry about that too much on this. Again, the fuse is right here. Yeah, could something short on this SL32? Maybe, but I highly doubt it. But if you want to do this mod yourself and you want to swap those around, more power to you. Go right ahead. You can do that. Now, I also rebuilt the Zobel network with a little bit better components. These are metal film resistors. They're the still 10 ohm, 2 watt each, and they're in parallel to give you 5 ohms. And then you have the this 0.1 microfarad capacitor, but instead of being like a lower end 50 volt one, this one's 630 volt. I think the one that was in there was maybe 100 volts. I'm not sure. This is a really good quality Panasonic capacitor, so these aren't going to ever go bad. And then here is right there is your snubber network that comes right after the Zobel network, and you can see it right there in a schematic. And as I showed you, this is 22 turns of number 18 wire. It's magnet wire on a 1/2 inch form. So I just took a 1/2 inch drill bit or a 1/2 inch little piece of tubing, and I don't know if I have it here, the form that I used, but and I wound it around there. When it was done, it looked something like this. You have to really pull tight on the wire to get them to stay together. If not, it'll get all springy and spongy. And then the resistor, I just passed through the center here and connected the leads at each end, and then just put a piece of heat shrink over it to hold it all together and keep it from moving, and to keep it from scraping through the enamel and all that. These will not get hot. You don't have to worry about any of that, and that'll take care of any kind of weird oscillation problems at the speaker terminals. For the wiring, it comes out of this, out of the amplifier. You can see one wire here, the other wire here, these two blue ones. They go down to the speaker protect board, which is right here. I'll pick it up so you can see it here. Hold on. There's your speaker protect board, and there's the blue wires going in. They come out here. I just followed the original wire harness that they built, and then it comes out of the 2 yellow wires and goes to the speaker network over here. And that's how I wired it. And no, I don't know who Pam is, but I'm sure she was the one that inspected this. So any of you who knew Pam, a lot of you seem to know Bob Carver and phase linear and all these history things. Let me know if any of you heard of who Pam is. Here's our 12,000 microfarad capacitors, and they take the place of these Sangamo 5900 microfarad caps, and look at the size difference. These are more than double the capacitance and higher voltage, and look at the size difference. Really have come a long way. But those Sangamos were still good. They were in good condition. They tested very good. Everything in this amp tested very good, believe it or not, other than these wires breaking off every time you breathe on them. I mean, that was the Achilles heel, is the quality of the build with this really flimsy board and these really old crusty wires that needed to be re-terminated. Everything else, though, this is, believe it or not, it's pretty good quality. I like this thing. Okay, before we begin testing on this amplifier, I want to do one last thing, and that is to check these transistors. And believe it or not, these are all original phase linear XPL 909s, with the exception of these 4 across the top, which these I believe are the driver transistors, and those 6 down at the bottom are the outputs, and they are originals also. Now, one thing to note, the earlier models of these, like the Series 1s, or if you want to call them that, this is a Series 2, they used traditional mica pads and grease, which is a good thing. Later on, they went to these sill pads on these. See these little red sill pads? They don't require grease or anything, so they're really easy to install. But you have to remember that these old transistors, especially these XPL 909s, they have that thicker case style, and they have sharp edges on them around the edge, unlike these RCA transistors that are a little bit softer edges on them. And if you over tighten these screws, they had the tendency to cut through those sill pads. So you have to be really careful not to over tighten them, but again, to make sure they're tight enough that it makes good contact with the heatsink. Again, you want to check that. It's not necessary to remove the sill pads and replace them, but you do need to check them. And if any of them look like they were over tightened, you can tell because the sill pad will start curling away from the heatsink and kind of wrapping around the edge of this, and you'll see where it'll kind of make a crease there. That's what you got to watch for, because once that cuts through there, the transistor could short to the heatsink. So, and there's a service bulletin by Phase Linear to that effect. Now, I checked all these sill pads just visually. They all look good. And then I also checked the mounting screws, and you're going to need a long driver. You can see I have this one that's extendable, so you can extend it, and then it'll fit in there a lot easier to tighten. It's a 1/4 inch drive nuts. So these have not been over tightened. Most of them were good. And like I said, the sill pads are in excellent condition, so I see no reason to replace them. So I can put this back together, and this amp is ready for testing. Okay, to set the bias on this thing, it's a little bit confusing to find it, but it's really very easy to do. So this is a Class B output stage. In other words, it's not like Class AB, where the outputs are sitting at kind of an idle current. So if you try to measure across the emitter resistors on the output transistors of this, you're not going to read anything. That's how these quasi-complementary amplifiers work. Voltage-wise, they're just at the turn-on point of the base voltage of the transistor. They sit right there at that, right at about 0.4 volts, 0.3 volts, and then they operate in Class B. So really the only transistors that have standby or idle current or quiescent current are the driver transistors, which are those 4 that I showed you earlier when we were looking at the outputs, those RCA transistors. Those are the only ones that are going to have bias current on them. So all you're going to do is there's a 10 ohm resistor, and it's located right here. So these are those RCA transistors. These are the actual drivers for these, what is it, XJ119 or whatever they are, the outputs. And you notice there's a 10 ohm half-watt resistor. You're just going to hang your meter across that, and you're going to adjust this bias adjustment until you get somewhere, and I put a note here, somewhere between 350 and 400 millivolts, which is the turn-on for these guys. So as you can see, on the one channel, I have it connected. I don't know if you can see down in there, but the resistor itself is kind of hard to see without some light on the subject, but it's right there. You see it down in there? Right about down there? There it is. So, kind of right where I'm pointing here underneath. It's very hard to see. I don't know if I can move this out of the way a little bit. See it? You can see that brown piece of tubing that goes to the lead of that 10 ohm resistor. So I'm connecting right here and here. See that? So if I back off a little bit, you can kind of see where I'm at. And all we're going to do is you just let the amp warm up, and you check the voltage. And let's get you on here on the potentiometer. Check the voltage, and you can see this one's already within that 350 to 400 millivolt range, and you adjust the pot right here until you get that 350 to 400 millivolt range, and it'll drift around a little bit, but it won't be too bad. And remember, the transistor that we have attached to the heat sink here, which is down below, that we swapped out with the TTA00 or TTC004B. That's the actual transistor that's handling the bias for this. So that's what you're adjusting for the VBE multiplier circuit. So then we would move over to this other one, and this one's a little easier to see. And right here is that resistor, so you can connect on this lead of this resistor here, because they go to the same point, and this over here, and set your 400 millivolts there as well. That's it. Simple as that. Okay, so I've done all the modifications and things to the amp and put it together. But first of all, let's just test this thing and see how it performs. Now, I do have a little bit of an instruction manual, or at least a spec sheet, and it gives you a test procedure, which I'm not going to follow this whole thing, but you can do that if you want. But I'm just looking for some of the specs they're looking for. Number one, with no load, they want to make sure that you have a symmetrical clipping, so with no speakers connected. And I actually looked at that off camera, and it's perfect on that. So we're going to kind of get to the meat and potatoes here. We're going to check the distortion, and we're going to look for we're going to set this for 40 volts RMS. We're going to verify that our harmonic distortion does not exceed 0.9%. Okay. Now, strangely enough, it doesn't tell you to change anything here, so I'm assuming they want you to look at a 2 kilohertz signal, but I don't know. Instead of one, most spec sheets always spec an amp out at 1 kilohertz, but we'll try 2 kilohertz and 1 kilohertz. Right now I'm set to 1 kilohertz. I'll run the amp till we get that 40 volts RMS, and then we'll see what we get. Okay, here we go. Turn on. Right now I'm only at 29, so let me increase this. Give me a second. Okay, there is our 40 volts, 39.9. And if we go over to our THD meter, 0.06. So we're actually better than the spec. We're at the same spec now, but at 2 kilohertz, and it's just a little bit over spec. See, it's 0.92 THD. Okay, we're now set to 200 hertz, so we're at lower frequency. And if we look, we're blowing it away on that. Look at that distortion figure, and that's at 200 hertz. Now, setting this to 20 hertz, you can see the waveform looks really good. We have just a tiny little bit less output, and that's kind of the roll-off of the amplifier itself. That's good. My meter, unfortunately, the distortion meter does not like low frequencies like that, but it is what it is. Okay, looking at 10 kilohertz. Yeah, very, very low distortion. And you saw from the waveform it looked really good. Switching over to 20 kilohertz. Again, looks really good. And my distortion meter is not reading it, because, of course, it's outside the range of the meter. Also, some of it has to do with the filtering I have set on the Keithley, but even messing around with it, it does not like super high and super low audio frequencies. And we're now going to do our sweep test. And the idea of this is to make sure that the amplitude never changes. So let's hit that. I really should. There. And the idea is these should never change. And let me overlap these over top of one another. There. So both channels should have the same output, and you shouldn't have any breathing in that waveform. It shouldn't breathe up and down. And you can see it's holding perfectly. So that's just showing you that the frequency response, and you can see at 20 kilohertz, it shrinks a tiny little bit. And that's just the nature of this amplifier. There's a little bit of roll off. You can see down here the voltage is staying within, you know, we're talking within 1 volt RMS when we're at 20 volts. So that's pretty good with the same input. Okay, let's look at our square wave. And you can see there's absolutely no ringing whatsoever. And if I try to stretch this out, and I'll stop it. And let me get some measurements up there. Okay, so looking at the measurement, it's not too bad. It's about what I expected for this type of amplifier. If we look at a change, because you just want to get above the knee point of that. As I know they have a percentage where they measure it. I always measure it right at the knee point, the bottom knee and the top knee. So the voltage change from here to up here is 32 volts. And the time that it took to move that 32 volts was 4.32 microseconds. So if you take the 32 volts divided by the 4.32, you get 7.4 volts per microsecond. So, and yeah, they use different units down here, but it's about 7.5 volts per microsecond, a little over 7 volts per microsecond. And that's about what you would expect for this type of amplifier. Really good amps, you know, fast amps can do double that. They can do upwards of 14. But again, the slew rate, it's a subjective thing after a certain point. 7 volts is where you need to be within that frequency range. Now let's look at where the high frequency roll-off starts to happen on this amp. Okay, I'm going to set 20 kilohertz, and I have it set that it's just touching the second graticule above and below the center line. So that's giving us about 13.4 volts. So we're not pushing this thing real hard. And what I'm going to do is I'm going to start running the frequency up in 10 kilohertz. At first, we're going to do 10 kilohertz steps until it starts dropping. Okay, so there's 40 kilohertz right there, and you can see we have our little drop. And so it's rolling off pretty smoothly. There's 100 kilohertz, and you can see there's quite a bit of roll off, but look, there is no distortion hardly at all, even though we're outputting 100 kilohertz. Yes, it's about half. So, you know, what is that, 6 dB? Do the math. I suck at that right now, but take a look, and back to 20. So, and this amp holds together. So you notice there was absolutely no ringing or anything like that, any kind of parasitic oscillation. If we switch over to square wave, you can see as you go up in frequency, it's going to start rounding off and turning into more of a sine wave, because that's the problem with the slew rate. We're at 60 kilohertz right now. You can see down here, and you can see how it's no longer a square wave. That's a result of the slew rate. And even if we go down to about 20 kilohertz, it just can't hold a perfect square wave at that frequency. Now, of course, a sine wave, you got it. And that's the whole purpose. Like if you're somewhere around that, you know, that 7 volts per microsecond range, you're going to hear the audible frequency range pretty good. I mean, there's not going to be much distortion at all. And again, this little bit of roundness at the bottom is because my left and right channel aren't perfectly lined up with one another, but pretty close. Okay, I'm not going to run this test real long because we're going to drive it into hard clipping here. And what you're going to see is the overload circuit start acting. And what we want is symmetrical clipping for number one. And we don't want to see any really crazy looking oscillation. So here we go. And it's clipping at 45.5 volts. And you can see just a little bit that fold over there that you're seeing is from the overload circuit. So what is the overload circuit? So what you're seeing is the action of these two transistors. So what they're doing is when you exceed the maximum current or the maximum load of the outputs, these will start to turn on. Okay, and it's because you're seeing the feedback coming here from your outputs, and it's a voltage divider between this 180 ohm, this 3.9K, and this 1N4148. And when the voltage reaches a certain threshold, these will begin to turn on. And as they turn on, if you notice, they're directly connected by one voltage drop of a diode to the input of your drivers, okay, which are those ones that with the little heat sinks on them on the circuit board, the little black round heat sinks. And it's going to start squelching out the base of this transistor and the base of this transistor down here, which limits the drive into these. So you can never drive these into an overload situation. One of the tests they want you to do is short the leads together, dead short, and then drive maximum power into the output. And theoretically, these should kick on and they should force the thing to clip and prevent the amp from overloading. I don't do that. Just a scary thing for me. But driving it into clipping like that, we're seeing that. So what you're not seeing these distorting because they're overdriving. You're seeing these limiting that. And that's why you see that little blip at the top. It looks kind of like it's folding over the base signal into the outputs. So let me put you back on here and hit that again, and you'll see what I mean. You see that? That little bit of fold over there? And if I drive it harder, it'll just make it do it more and more. See that? And that's what it does. Now with all the testing we've been doing on this, 39.8 degrees C, 103 degrees Fahrenheit. This amp runs really cool, even when you drive it really hard. So I would have to say that we successfully tamed the flame on the Flame Linear. And this amp's going to work great. Okay, so we'll end this with a little bit of music. I'll do, let's play Mirage. I haven't played that one in a long time. It doesn't have a lot of bass and kick drum and punch to it, but it's just so clear, and it really expresses kind of what this amp is best at. This is a very powerful amplifier. It can definitely reach down very low, and and it's really good with the bass. But the thing that I like the best about this is how it is not fatiguing on the ears. This is a really clear sounding amplifier. It's not harsh, and it's one of those things you could turn it on and listen to it all day and your ears will not get tired. So let's end the whole series, or this series, with this, and I'll play that song. And as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll be back with the next one, the Model 700, and it's going to be a little bit different than this one because I think I may do some different things with it than I did with this one. So again, we'll see you all soon. Take care, everybody. Bye-bye.